So I'm working out of the OpenStax Statistics Chapter 8 problems. So in this example, we're going to talk about comparing different confidence intervals with the stats exam scores. So you can reference the book for free. Just look in the description of this video and you can get a link. And then if you want to access the Excel worksheet for free, just go to divideandconquermath.com and go to the OpenStax Statistics section, and everything you see in this video you can download for free. Okay, so with these examples, so basically what we're doing now is we're changing up some things about finding our confidence interval. So remember that with the original example, that was from the first tab. So we had our 36 exam scores and they had a mean score of 68, and we had a population standard deviation of 3 points. So in the first tab, we had to find a 90% confidence interval. And now we have two different kind of examples here, just asking us to change up a few things. So suppose we change the first example by using a 95% confidence level. So now we're going to find a 95% confidence level for the true population mean statistics exam score. Okay, so what I've done to make life easier is I went ahead and I just copied all the calculations from the original problem. And so now I'm going to do this 95% confidence interval. So the things that you kind of have to think through here is, so to find the 95% confidence interval, what of this data really needs to change? So the given data won't change, but it's the alpha level that is going to change. So my alpha in this case, I'm going to take my 1 minus my 0.95. So you always take 1 minus whatever the confidence interval level that you want is. And so I talked about this also in previous tabs. It's kind of up to you. If you want, you can immediately take that alpha value and divide it by 2. It doesn't really matter if you want to do that or not. The main thing is that you have to eventually divide it by 2 to find your critical value. So to find the critical value, I use that norm.s.inverse function. And so either I can divide my alpha by 2, or I can take my alpha that I divided by 2. So it doesn't matter which way you want to do it. And remember, for your critical value, you always need to have the absolute value of your critical value. So I'm going to take basically I just always need this number to be positive, right? And I've talked about that more in the previous 2 slides. Now, another thing that your book tends to do, your book does tend to round this number. So you can also round this. I tend to like to round it to 3 places. So I get 1.96, so I'm going to use that as my critical value. Okay, so that changes, and since that changes, that's going to give me a new error bound. So for my error bound, I take my critical value times my standard deviation divided by the square root of n. So there's my new error bound, and then from there I'm going to get a new confidence interval. So I'm going to take the high versus the low parts of my confidence interval. So for that, for the high part, I take the mean plus my new error bound, and then I take the mean minus my new error bound. So here's my new confidence interval. And so the confidence interval is, in this case, 67.02 to 68.98. So that's the confidence interval in this case. Okay, so now let's pivot to the other question. So we're going to leave everything the same except for the sample size. So we're going to use a 90% confidence level. What happens to the error bound if we decrease the sample size to n equals 25 instead of n equals 36? So now I'm going to change this to new sample size of n equals 25. Okay, so looking at this, my critical value in this case does not change, so I can recycle this critical value. But I am going to have a new error bound because I'm using a new sample size. So what I'm going to do is I'm just going to write, I'm going to write n. I'm going to just write n as 25 here just so I don't forget. And now I'm going to calculate a new error bound. So for my error bound, like I said, I can recycle the original problem's critical value. That's not changing. My standard deviation is still 3. And then I'm going to divide this by the square root of my new n, which is 25. So here's my new error bound. So from here, I can go ahead and calculate my new confidence intervals. So I'm going to do my high versus my low. So I'm just going to recycle the mean from before, plus my new error bound using that new n. And then I'm going to take the mean minus, again, my new error bound. Okay, and so now in this case, I have the confidence interval is going to be this 67.013 to 68.987. Okay, and so now what we can do here is we can kind of compare these three different values and like how that kind of changed things. So this is the interesting part of doing all of this work. So at the end of the day, the whole point of what we're trying to do is we're trying to figure out what is a good range for what the actual population mean is. Because remember, the idea is if I were to take a sample of 36 anything, right, and calculate the mean. So if 10 of us went out and gathered data of size 36, none of us would get the same mean, right? So there's this idea that we know that from every sample size that you draw, everybody's going to get a slightly different mean. And so the whole idea then is, so if I wanted to have a range, a decent range that might tell me exactly what the true population mean is, not my sample mean that I keep finding, but kind of where does that true population mean lie? Well, at the end of the day, it's kind of a thing of like pulling different levers. And it's up to you as to how refined you want to make it. So with our original problem, we were 90% confident that the true population mean fell somewhere between 67.1775 and 68.8225. But that idea of being 90% confident, that is, that's kind of like an arbitrary number that you choose. And 90% confident might not really sound that great, right? So this seems like a very narrow interval here, but you're only 90% sure of it. And depending on what you're talking about, you might want to be more sure. So notice what happens though if I try to increase my confidence level. So if I say want to be 95% confident, what happens? Well, this confidence interval, this is actually wider than the 90% one, right? So if you want to be more confident, you're probably going to give yourself a larger range, right? And that's also going to indicate that with our critical value, so when we have a smaller alpha that we're working with, we end up getting a higher critical value. So you can kind of see how that works when you're playing with the standard normal distribution. And the other thing that's going to impact our confidence interval is also the size of our sample size. So also just notice, so here was my 90% confidence interval with 36 data points. If I were to change this to just be 25 data points, what happens? Well, this also will force ultimately my error bound. So I'm dividing by a smaller denominator, so I have a larger error bound. And this will increase the size of my confidence interval. So as far as like, what's the right way to set up a confidence interval? Well, it depends on the information that you have, but things that you can say for sure, the larger your sample size, that's going to kind of help give you a more narrow confidence interval. But the more confident you are, right? So this was 95% confident. The more confident you are, the wider your actual interval gets. And so it's one of those things with statistics where it's like, okay, it kind of depends on what you're talking about. The context is what really matters. They're all kind of in that same range. And so it can be a little bit of just a personal choice as to what type of confidence interval you want. But also it could be, the context is really going to matter as to which one of these factors are going to be the most important to you. So it's just an interesting thing to note of how small changes can impact your confidence interval. And it's just something to think about as you're kind of moving forward.